Go over this Lagrange multipliers problem again. So we have this x squared plus y squared function that we want to optimize. Really, I should have started at this page. We have x squared plus y squared. We want to optimize that subject to this constraint. So this means f of xy is going to be x squared plus y squared, and g of xy is going to be what I have here. Now, typically, it's going to be a word problem, and you're going to have to figure out what f is and what g is, but I pretty much gave it to you in this problem. Okay, so the first step of Lagrange multipliers is to set the gradient of f equals to the lambda times the gradient of g. Okay, well, once you figure out what f is, the next step then is to set the gradient of f is equal to lambda times the gradient of g. And in this problem, this is what you get here. Okay, and remember we saw that if you add the first equation to the second equation, or the top equation to the bottom equation, and then subtract it using the symmetry of the gradient of g, you get something nice. In particular, you get that x plus y is equal to lambda over 4 times x plus y, and you get that x minus y is equal to 2 lambda over 9 times x minus y. And that's what we have recorded that in the next screen over here. So now the equations involving Lagrange multipliers are just equivalent to those. Okay, and then this is the constraint equation. So I'm going to deal with the red equation. So there are two possibilities: x plus y is 0 or x plus y is not 0. If x plus y is 0, then x is equal to minus y. Okay, so I'm going to take this value, this expression that relates x and y, and I'm going to plug it into the constraint equation. And this is what I'm going to get when I do that. I get 4x squared over 9 is equal to 1, and so this tells me that x is equal to plus or minus 3 halves. And that's just because if x plus y is equal to 0, this term is equal to 0, and then this term right here becomes 4x squared. So I get x is equal to plus or minus 3 halves. Okay, so that gives me 2 points. X is equal to minus 3 halves and y is equal to 3 halves, or x is equal to 3 halves and y is equal to minus 3 halves, because x is equal to minus y. So that handles the case in this red equation where x plus y is equal to 0. Now the other option is x plus y is not equal to 0. In this case, we can divide both sides of this equation by x plus y, and what we end up with is the following. So lambda is equal to 4. Since I can divide both sides by x plus y, then I get 1 is equal to lambda over 4, so lambda is equal to 4. Now if I take that value for lambda and plug it into the blue equation, what I get is the following. Now the only way this equation can be true is if x minus y is equal to 0. So now I have x minus y is equal to 0, which is the same as saying x is equal to y. And I'm going to plug this into the constraint equation to get the... Okay, so 4x squared is equal to 1. This means that x is equal to plus or minus 4. And the solutions that we get from that are... So I'm sorry, what I meant to say is the solutions that we get is x is equal to 2. Since x is equal to y, x is equal to plus or minus 2. Since x is equal to y, what that tells us, since x is equal to y, this tells us, well, if x is equal to minus 2, y is equal to minus 2. If x is equal to 2, then y is equal to 2. So the 4 points that we need to test are these 4 points: minus 3 halves, 3 halves, 3 halves, minus 3 halves, minus 2, and 2, 2. Okay, so f of minus 3 halves is equal to 9 halves, and similarly f of 3 halves minus 3 halves is equal to 9 halves, and then f of 2, 2 is equal to 8, and f of minus 2, 2 is equal to 8. So 9 halves is the absolute minimum, and 8 is the absolute max of f subject to this constraint. So if all of the points lying on this rotated or tilted ellipse, this gives you the smallest and this gives you the biggest. That's only for points on the ellipse.